Hello, this is Alexander Herr. I am in Group D, and this is our project. The people in Group D is me, Alexander Herr, Brenda Perez, Paulina Esguerra, and Adrina Martinez. And this is our first experiment on salinity. Now, the question that we chose was, is the accuracy of the fluval sea hydrometer affected by the temperature of the exhibit water? We wanted to conduct 3 experiments on the exhibit water, and the exhibit water that we're using is salt water actually, and the salt water that we're using is from the otter exhibit from the Fresno Chaffee Zoo. We wanted to conduct 3 experiments, one at room temperature, one at below room temperature, and one at above room temperature to determine if the result of the exhibit water changes based on the temperature. Of course, our research question again is the accuracy of the fluval sea hydrometer affected by the temperature of the exhibit water? Our experimental design will include using the fluval sea hydrometer. We're going to measure the parts per thousand and specific gravity to find out the density of the solution at various temperatures. We're going to find out if the fluval sea hydrometer is accurate before experimenting, because by doing this we know that our results will be as accurate as possible. We're going to conduct experiments at different temperatures and record specific gravity and parts per thousand. Now we wanted to do the perform an accuracy test of the fluval sea hydrometer to make sure that the results that we're getting were as accurate as possible. So we used 100 milliliters of water, and we measured that by using a volumetric pipette. And however, our fluval sea hydrometer actually only fits 75 milliliters. We still used 100 milliliters. We did three tests. We did one at 0 grams of sodium chloride. We did one at 2.31 grams of sodium chloride, and we did one at 4 grams of sodium chloride. Now the solution for parts per thousand is solute in grams divided by the total mass minus the mass of the container. And of course, before we did this, we actually measured the mass of the container in grams because we needed that. So in the 2.31 gram solution, we found that we did, of course, 2.31 grams of solute, which is sodium chloride, and the big number there, 100.034 grams, is actually the flask with the salt solution in it, minus the mass of the container. And from there, we got 25.029, or if we were to round it to the significant numbers, it would be 25.0, or just 25 parts per thousand. The 4 gram solution is a lot bigger because the solution was the total mass of the solution was actually a lot bigger than the last one. So from there, we actually yielded a bigger number in parts per thousand. Now, these numbers that we're getting first is the true value. This true value is what we're going to be using in the percentage error formula. Now, to find the experimental value, we need to pour the solution that we measured in the hydrometer. When we poured it into the hydrometer, the 2.31 gram solution read 23 parts per thousand, and the 4.0 gram solution read 40 parts per thousand. Now that we have the true value and we have the experimental value, we can go ahead and use the percentage error formula. Now the percentage error formula is the experimental value minus the true value divided by the true value times 100. And when we did that, first we did the 2.31 grams sample, and we got 23 parts per thousand minus 25 parts per thousand divided by 25 parts per thousand times 100. Sorry, my mistake. And we got a negative 8% error. Now, when we did the 4 gram solution, we did 40 parts per thousand, which is the experimental value, minus 42, which is the true value that we got, divided by the true value, and we got a negative 4.8% error. Now, these percentage errors are really small, so we concluded that this could be accurate enough to conclude that the results that we get from our experiments would be credible enough. Now, so when we tested the samples at 3 different temperatures, we used a temperature measuring device, a thermometer, and we put it into the sample as it was changing temperature. So at room temperature, it read 30 parts per thousand and 1.022 specific gravity. Below room temperature, at 15 degrees Celsius, it was 24 parts per thousand and 1.017 specific gravity. And above room temperature, which was used by the Bunsen burner, we got 33 parts per thousand and 1.024 specific gravity. Now these numbers are completely different, and we can kind of already make a conclusion from this. But before we do that, we need to calculate the density over the different temperatures. The specific gravity equation is the specific gravity equals the density of solution divided by the density of water. As we know that the density of water varies on the temperature that we're using, and we're measuring density of water at 15 degrees Celsius, 20 degrees Celsius, and 33 degrees Celsius. So now that we have that, we can arrange the equation to find the density of the solution, which is the density of the solution equals the specific gravity times the density of water. When first we did 15 degrees Celsius, and the specific gravity that we got earlier, we used that, and the density of the water at 15 degrees Celsius is 0.9991 grams per centimeter squared, and from there we got 1.016 grams per centimeter squared. At 20 degrees Celsius, the density of the solution equals 1.022 specific gravity times the density of water at 20 degrees Celsius, which is 0.9982 grams per centimeter cubed, and we got 1.020 grams per centimeter cubed. At 33 degrees Celsius, we got 1.024 specific gravity times 0.9944 grams divided by centimeters cubed, and we got 1.018 grams per centimeter cubed. Now that we know that, we decide to graph it out, and we see that the change in density or the temperature change does have a huge effect on the density, whether it may be decreasing the density or whether it may be increasing the density. And so therefore we conclude that from our results that if we change the temperature of the saltwater from the otter exhibit from the Fresno Chaffee Zoo, that we can see a change in the density of the samples. Since from this observation we can assume that as the density is changing, the density is changing as we change temperatures. We can see a change in the accuracy of the examples because the density is changing and it's not constant. Thank you.